solving a question from the lead code, and this question came in daily questions of the lead code, and the question is linked list in binary tree. So it is based upon the linked list as well as the binary tree. Trust me, the question is very simple. We'll try to solve the question, and we'll also try to understand that how we can get the integer for the questions, and yeah, so let's get started. And the question states that we're given a binary tree root and a linked list with head as the first node. Return true if all the elements in the linked list starting from the head correspond to some downward path connected in the binary tree. Otherwise, return false. In this context, downward path means a path that starts at some node and goes downwards. Now, we are also given some certain examples here. So the example is that, we are given a linked list 4 to 8, and we are given the root that is the root of the tree. We are supposed to find a path which has the values in the order of this linked list as 4 to 8. And as we can see, it's highlighted in the blue curve 4 to 8. We find this path, so we return true. Another example here. So 1428, 1426, and that is from here 1 to till end. So we find this path from the root till this leaf 6, and so we return true. Now, imagine that imagine that we are given here 14268. 14268. So in this scenario, 14268 comes this side. And so this won't be a path because path is something that is totally leading towards the downward, that is towards the leaf. So since it's not totally down, leading towards a single down, or in a single direction, but it's going in the two directions, the left and the right. So this won't be a path in that case. The case is when there would have been 1426 and additional 8, right? So let's try to come on the notepad and try to understand how we can get the solution. So yeah, so we are here and we can find out. Imagine that we are given a linked list of you know we are given a linked list like this, mm, like this, and we can assume this first example where our head was 4, 2, and 8, and we can assume this, this particular image. Let me try, yeah, this particular image, yeah. So let's try this example. So we can assume this image here, and this can be simply deleted from here. Okay, yeah. So we can here check out this, right? Now, if we somehow observe, if we can observe here, let me take the red pen. Yes. So what we can do is that, we are supposed to find out a path in the tree where the values are in this order. First is 4, then 2, then 8. Now, let us check the constraint. What is the constraint here given in this question? Constraint is that there can be at max 2,500 nodes, and there can be less of uh, s- linguist at max 100. So, it is allowed that it is totally fine if our solution goes up to n square, where n is nothing but the number of nodes. where n is number of nodes. It's totally fine, right? So where n is nothing but this. Okay. So let us take this particular now and also take this example here. All right. So what we can do is we can simply here we can here simply, try to convert this 4 to 8 in the form of a string, then it will become 4 to and 8. So we can try to convert this linked list into the form of string, and it will become 4 to 8. And we can simply traverse through the, DFA. We can simply try all the paths of this tree. That is one, 4, 2. This is one part. This is another. Then one path will be this, and one path will be this. So we can try all these four paths leading towards the leaf, and while checking towards all the paths, we can simply check that, and simultaneously we'll be maintaining the val the while traversing through the path, we will be maintaining a string as one, like as one, four, two, and one for this particular path. Okay, so for this particular path, and we can simply check it out if it is equal to this 1 4 2 1, and 4 to 8, is this equal? No. If this is not equal, then we can simply explore the next path. And if it is found that is equal, this the string is equal to the path, then we can simply return true. And or we can simply store in a variable as true, and we can return that variable. Now imagine that the path is not starting from the root, because we are traversing through the path right from the root, but but the the string which we are trying to match is somewhere beginning at after the root, like in this example, as like in this example the path is starting from this after the root. So in that scenario our string is going to be 1 4 2 and 8. So we see our string is this. Since our string is this, we won't be able to, check if it is equal to not without removing this one. So we'll have to remove this one that is from the root, and then we'll have to check if it is equal. So what we can do is that since we will be traversing through the path and we will be storing the path values in the form of the string, we can check, we can take the string from the end and keep adding to the string, right? Like for example, we can take 8, we can check if it is equal to this 428 now. We can check, we can then add 28 to it, then we can check if it is equal to this or not. No, it's not equal. Then we can take this 4 and check if it is equal to this 4 to 8 or not. Since it's not equal, we can simply return. Since now, yeah, sorry. So since it's equal to this exactly string, so we can return true or store in the variable that we have found a match. This is how we can solve this question. Now, what we can do is we can do a dry run of the question and walk through the code. So let's take this example. We can take this here, and this is going to be our head. This is going to be our head, right? We have found this as our head here, and we can do a try run. Okay, so our first task here is nothing but to, to convert this to convert this link list into the form of the string, and then we can simply traverse with the path, and we can check it out if it's matching or not. So let's first try to convert this into the form of the string. Right now, how we can convert this into the form of string? We can simply traverse through the head, because I guess traversing through the linked list is pretty easy, and we can simply traverse. Then our string will be 1, 4, 2, and 6. So we have traversed through this. This is our string. All right. Now we'll be exploring to this DFS. We'll be exploring to this, traversing to this tree through DFS. So how we can do that? We are here at the root. Now our string is here as, so this is the first iteration. This is the first pass. Right. So we are here at 1, and we can simply traverse to this 4 via like this. 1, then we'll be going to this left part, it will become 1, 4, then we'll come to this path, which will become 2. And we are, guys, we are checking every time whether it's correct or whether it's matching or not. So since it's again not matching, we're simply, putting it 1, then it's 1, 2, after 2 it's 1. So if it's not matching, since it's not matching, we are simply going to, you know, we won't be doing anything because we didn't get any match, right? This didn't work out. Now, our second traversal towards the path leading to leaf is 1, 4, then it's 2, then it's 6. Right now, since we are checking every time, now when we will check, is it matching to this string? Yes, it's matching to the string. The string, what we are looking for is matching with the string. Since we got a match, so we are going to change the variable that is it possible or not as true. Is possible is possible as we'll mark it as simply true. And we can then return. So it's pretty much easy question. We don't have to stress a lot over it. So let's try to understand the code, and code is pretty intuitive and easy to implement. So we have taken a string, empty string, then we are simply, taken a temporary, a temporary node which is heading towards this head. And while it's not empty, we are simply, you know, adding the string, extending the string from 1 to 4 to 1, 4 to 6. So after this, it will become 1, 4 to 6 in case of second example. Example. All right. Now we are just supposed to do a DFS traversal you know, through the code. That is, we are passing the root, that is the reference towards from to the root of the tree, the string s, which is going to store the path in the form of the string, and the string head, which is the actual, traversal, the values of the linked list. So this is how we are adding to the string. We are extending the path. We are checking that if we are only comparing if the length of the string of the path and the length of the head uh, that is of the for the linked list is equal to or is greater or equal to or not. If it's more, then it's not of use because it's not there's not going to be any sort of match then. Now we are simply checking for the backward of the string. As I said, we'll be simply checking for the backward. We will be taking this 6. Is it equal? No. Then we'll add to this. I'll add this 2 to the 6. Is it equal? No. We'll add 4 to this 2. Is it equal? No. We'll add 1 to the 4. Is it equal? No. Why are we doing this? We are doing this because there is possibility that the path we are trying to match is not, it might not be starting from here, root of the tree. In this case, we are supposed to simply check from the backward direction, because even if in that case our path is starting from this 4, we will able to make a match. All right. So we are doing that, and then this is simply, we are calling, we are simply checking if the root, if the left part of the root is not equal to the null, we're simply calling to the left node, and if the right node of the root is not null, we're simply calling the right node, and this is how it works. And the code is, pretty simple to implement. I hope everything's clear. If you talk about the time complexity, then the time complexity for this solution uh, is big O of n square. Why n square? Because we are traversing through the string right from the n every time to check if it's matching or not. And the worst case, it can be, there can be to 2500 square nodes. That is again within bound. So that is nothing but 625. So it's again within the boundaries of the time complexity, so it works. If you want, further improvement, we can